right, so with that in mind, let's take what we have learned so far and apply it to an example problem with even more complexity. I would like you to draw the orbital box diagram for the 15 electrons in the element of phosphorus. In addition, in much the same way that we just did with carbon, I would like you to pick out what are the 4 quantum numbers of the 15th electron that gets placed into phosphorus. All right, welcome back from unpausing. I hope you actually attempted working out, illustrating what the orbital box diagram for this phosphorus was and determining what its quantum numbers were, at least for that 15th electron that gets placed. So let's just do this together. There are 15 electrons inside of phosphorus, and each one of them is going to need a home. So we are going to start with the lowest of the low, the 1s orbital. We're going to take 2 electrons, put it into the box. After that, we have the 2s orbital. Similarly, we're going to take 2 electrons, put them into this box. So far, we have placed 4 of the electrons, and we have 11 left. Well, after the 2s, we get that 3-for-1 deal. We get all 3 of these 2p orbitals, and we're going to have to place 6 electrons in each of these orbitals. 1, 2, 3, spreading them out first, and then 4, 5, 6 inside of each of, or 2 electrons inside of each of these boxes. Well, after 2p, if you didn't pause the video or scrub back to see the Aufbau principle diagram, which again I'm going to clean up, boom, we've placed 2 electrons in the 1s, 2 electrons in the 2s, 2 electrons in the 2p, and we can see in our diagram next what comes is the 3s orbital. Oh, too far. Here we are. Spoilers. All right, so the 3s orbital is what comes next. 3s box, 2 electrons inside. So far we have placed 2, 4, 6, 8, 10, 12. Suddenly I just couldn't count by even numbers. 12 electrons placed. This means we still have 3 left that need a home, and after the 3s in the diagram, if we were to look back, we would see comes the 3p. Now, much like the 2s, the 3p is also a 3-for-1 deal. We're going to have to draw each of these 3 empty boxes, even if we end up not placing an electron in one of the boxes. It's just a great habit to get into. All right, so our 3 electrons, we have 3 left. Each one of them, according to Hund's rule, we are going to spread out as much as we can. Each of these last electrons spreading out in the degenerate orbitals, each one getting their own identical but separate homes. All right, so hopefully this is also what you got. You probably had more space to actually draw the 3p up right next to the 3s, but again, I write large, so I ran out of space. The last thing that we were asked to do was to identify the 4 quantum numbers of this 15th electron, the last one that was placed in all the boxes. So I'm going to draw that right up here. Now we are going to follow, again, the N, L, M sub L, M sub S format. So first and foremost, we need to identify what shell the electron is in. In order to figure that out, all we have to do is look at the label on the orbitals that we're working with. 3p means that we are working with a 3 for the N and a 1 for the L. Now the M sub L, this is again supposed to represent the orientation of our orbitals in 3D space. Which of the 3 you choose doesn't quite matter, but by conventional standards, when we're working with the p orbitals, we label the M sub L is equal to -1 as the first box, the 0 is the central box, the +1 is the third box. So again, since each of these are degenerate, it doesn't really matter which of these 3 you choose because they're just relative or unique relative to each other in 3D space. But just by conventional standards, we're gonna stick with that third box being equal to the +1 label. Now, last but not least, the electron spin, we can see the arrows pointing up. And again, this is technically a conventional standard that we draw the upwards facing arrows first. By all means, this could be like each of these 3 could be downwards facing, just so long as each of them are the exact same. It doesn't really matter. But according to conventional standards, we draw plus up, or the plus 1/2 electrons first, and then the -1/2 come after. All right, so our unique quantum number set for the last electron is 3, 1, 1, 1/2.